Fill in the gaps in the following table, assuming each represents a neutral atom. So we have the symbol for chromium 52. So if it's chromium 52, it has a mass number 52. Chromium is number 24 on the chart. So it's number 24 on the chart because it has 24 protons in its nucleus. So atomic number 24. So if I know what the atomic number is and I know what the mass number is, if I subtract the atomic number from the mass number, the difference between the two will give me how many neutrons I have. All right, so 28 neutrons. If it's a neutral atom and you've got 24 protons, you'd have to have a similar number of electrons to be neutral, right? That's the way electricity works, right? Same number of positive charges and negative charges. You cancel charge and you're neutrally charged. So this is the pattern we're going to use for answering these, filling in these boxes, right, to get a clue. And this way you're able to identify what the isotope is, right? So chromium 52 has got 24 protons, 28 neutrons, 24 electrons. So looking at the next one, they gave me the fact that it has 25 protons. So if you've got 25 protons, that means you're manganese. If you've got 25 protons and 30 neutrons, you're talking about manganese 55 with a mass number of 55. And if it's a neutral atom, if you have 25 protons, you have to have 25 electrons. So use the clues to figure out what the missing information is. So you can do the same for the rest of them. What is the mass in AMUs of a carbon-12 atom? All right, after much debate, it was decided that if you were going to mass things, right, weigh things, they had to be relative to something. So if we're going to weigh atoms, it was decided they were going to be relative to the carbon-12 isotope. So by definition, the carbon-12 isotope weighs exactly 12 atomic mass units. So the question always is with the other atoms, how much heavier or how much lighter are you than the carbon-12 isotope? And you put it on the scale, figure out whether you're heavier or lighter. So why is the atomic weight of carbon-12 reported as 12.001? The reason for this is not all carbon is carbon-12. Some of it's carbon-13. So what that 12.001 AMUs represents is a weighted average. The fact is 90-something% of your sample is going to be carbon-12. So it's going to be weighted towards, the weighted average is going to be weighted towards carbon-12, but some of the isotopes are carbon-13. So it's not going to weigh exactly 12. It's going to weigh a little more. So how do you figure out what a weighted average is, right? So you'd have to know what the different isotopes weigh, and you'd have to know what fraction of a sample they represent. So the only two isotopes of copper occurring naturally are copper-63. The mass of copper-3 is not 63, right? 63 is its mass number. You got to compare it to carbon-12 to figure out how massive it is. So it actually weighs 62.9296 AMUs. Right, lots of sig figs there, and if you had a sample, 69.17% of it would be copper-63. So for copper-65, it weighs 64.9278 AMUs, has an abundance of 30.83%. So the weighted average, you take the mass of the isotopes and you multiply it by the fraction that they represent of the sample. So most of our sample is copper-63. So we expect the weighted average to be closer towards the mass of the copper-63 isotope than the copper-65 isotope. So when you multiply the fraction by the mass, and add them together, you get the weighted average. Naturally occurring magnesium has the following isotopic abundances. Isotopes. So magnesium-24, roughly 79% of your sample is going to be magnesium-24, 10% of your sample is going to be magnesium-25, and 11% of your sample is magnesium-26. And these are what their actual masses are, right? So if I want to get the weighted average of magnesium, I would need to turn those percentages into fractions, multiply those fractions by the masses, and this would give me the weighted average. Now, looking at my sample, it's almost 79% magnesium 24. So my expectation is, when I do the weighted average, that my answer is going to come out closer to magnesium 24 than magnesium 26. And lo and behold, oh yeah, closer to magnesium 24 than magnesium 26. That's the weighted average. Grab a sample. This is what it's going to weigh. So where do we get these masses from? How do you get the atomic mass of these different isotopes? Well, the answer is using what's called a mass spectrophotometer. And it looks complicated. This is a very simple look at it. But what you do is, on the left-hand side, right, you're putting a sample in, and they say you ionize it, right? So you charge it positive, you run it through a magnetic field. Anything that has a positive charge is going to be affected by the magnetic field. Now, heavier things are going to be less affected, so they're going to go further downfield than lighter things. So if I want to get the mass, say, of chlorine-37, what am I comparing it to? I'm comparing it to carbon-12. So the first thing I do is zap these atoms so that they're charged positive, knock the electrons off so they're charged positive, and now run them through the machine. So because chlorine 37 weighs more, or is more massive, it should go further downfield than carbon-12. So based on the separation, how much further chlorine 37 goes downfield than carbon-12, we can get relatively how much more massive chlorine 37 is. So by definition, carbon-12 weighs 12 AMUs. Because chlorine 37 goes further downfield based on separation, we're able to get a measurement of how massive chlorine 37 is compared to carbon-12. So again, the point is, chlorine 37 doesn't weigh 37. If you want to weigh it, if you want to get a mass measurement, you have to compare it against carbon-12, running it through a mass spectrophotometer. Oh, here we go. So the last thing they wanted was, what would the spectrum look like if we were running the 3 isotopes of magnesium through the spectrophotometer? Well, since most of our sample is magnesium 27, we'd have a big peak, right? Frankly, running it through the mass spectrophotometer separates the isotopes from each other, right? So the lighter ones land further upfield, so we get a big peak at 24. We get a smaller peak at 25, and a little bit bigger peak at 26. And this is what the spectrum would look like for a sample of magnesium running through the spectrophotometer. Elements of group 4A showing interesting change in properties. Moving down to group, okay, so looking at the periodic table, can we predict trends? All right, so we're going down group 4A. Give the name of the chemical, the symbol for each, and label it as a metal, a non-metal, or a metalloid. So if you remember, right, we've got the magic staircase, right, the black staircase here. So as I run down group 4A, starting with carbon, I'm definitely on the non-metal side of the line. So carbon's a non-metal. Silicon kind of straddles the line. So if you're straddling the line, are you metal or are you non-metal? We put you in this category of metalloid, which means that you're not quite a non-metal, you're not quite a metal. Same with germanium. But tin, definitely below the line, right? So tin falls into that metal category. So if you're on the right-hand side of the line, you're a non-metal. If you're on the left-hand side of the staircase, you are a metal. If you're straddling the line, you're considered a metalloid. Number 41, what can we tell about a compound when we know its empirical formula? What additional information is conveyed by molecular formula, by structural formula? Explain in each case. All right. So by definition, what an empirical formula is just the smallest whole number ratio of the atoms in the compound. Now, for something like an ionic compound, that's all you need to know. what is the ratio of the cation to the anion, right, in order to differentiate the different ionic compounds. Now, with molecules, it's more complicated because you can have more atoms than the smallest whole number ratio, right? You can have double the atoms or triple the atoms. So with molecular formula, you're getting the actual number of atoms in the molecule. That's why they call it molecular formula. A structural formula, because molecules have different orientations of how the atoms are arranged around each other, you get what's called a structural formula. And molecules have a lot to do with what their geometry is, how those atoms are arranged around the compound, as to how they're going to interact. So with ionic compounds, all you need to know is the empirical formula. With molecules, you need to know the actual number of atoms, and you need to know how they're arranged in order to figure out chemically what they're going to do. Oh, here we go. So, for example, a perspective drawing, right, is one that gives you the geometry, right, how these atoms are orientated in space. In the case of methane, CH4, you've got a 109.5 degree bond angle between the hydrogens. So methane's a non-polar molecule because of how those atoms are arranged. It has a lot to do with what its physical properties are and chemical properties.